Today, I'm going to introduce the project that focuses on predicting abalone age using machine learning models trained on physical attributes. These are the analysis steps. Firstly, the analysis imports libraries that will be used later. And the second part is the data preprocessing part. Firstly, the analysis fetches the Abalone dataset from the UCI machine learning repository. After that, it extracts features and targets. X contains the feature data such as shell length, diameter, and other physical attributes of abalones. Y holds the target variable, which is the number of rings. Then it shows the descriptive information about the dataset. And then it do the exploratory data analysis. Firstly, we see the number of rows and columns of feature data. Then we check the number of missing values and duplicates and find that the feature data doesn't have missing values and duplicates. After that, we see the number of unique values in each feature and feature data from information. Then the analysis combines the features and target data frames into a single data frame called DF. Uh, this step, the analysis used the ultrawide library to automatically generate visualizations for EDA on DF. It generates the data quality report, the pairwise scatter plots, and many other plots. By using these plots, we can better analyze the data. Then it checks the skewness of feature and target data and find that target data has a right-tailed distribution. Then the analysis generates descriptive statistics for variables. And because sex is a category, categorical feature with no inherent ordinal relationship, the analysis performs label encoding for the sex column. Then it defines a function to identify outliers based on the Tukey rule and apply it to the target variable. It removes the rows corresponding to the detected outliers. This step can detect extreme values that can negatively impact model performance. After doing this step, we use box plot to check outliers in the range column. The third part is the feature importance part. The code creates a holdout sample by splitting the data into training and test sets before applying any transformations. 20% of the data is set aside for the test set. Split should be done before transformation in order to avoid data leakage and generalization. Then the analysis applies normalization and standardization techniques to scale the features and target variables. Firstly, it uses min-max scaling to rescale the feature values to a specified range. Then features and target variable are separately standardized. Scaling is applied because of several reasons. Firstly, later we will use algorithms like SVM and KNN that are sensitive to feature scales. Scaling ensures that each feature contributes equally to the distance calculation. Besides, scaling ensures features and targets have comparable ranges. The analysis used a random forest regressor to evaluate the importance of features in predicting the target variable and visualize the results using a horizontal bar chart. It evaluates feature importance in order to identify and drop features with very low importance to reduce computational complexity and overfitting. It helps understand which features contribute the most to the prediction. And from the bar chart, we can find that shell weight and shaft weight contribute most to predicting the target variable. The fourth part is to base learner regressors on holdout sample. Firstly, the code defines two functions for evaluating and visualizing the performance of regression models. Evaluation metrics include MSE, MAE, and R-square. It creates a scatter plot to visualize the prediction errors. Then the analysis compares several regression models to evaluate their performance on the test dataset. These models include multiple linear regression, lasso regression, ridge regression, KNN, SVR, decision tree, and MLP. In these chosen models, multiple linear regression has high bias and low variance, and it tends to underfit when data relationships are complex. And for decision tree, it has low bias and high variance. And pruning the tree can help reduce variance while maintaining interpretability. The analysis prints the regression coefficients for linear models. Besides, it calls the previously defined functions to evaluate and visualize model performance. It also computes the worst-case prediction. From the plots, we can analyze the performance of each model. For multiple linear regression, MSE is 5.1, MAE is 1.61, and R squared is 0.53, indicating that about 53% of the variance in the target variable can be explained by the features used. The scatter plot shows a positive correlation trend. However, there is noticeable spread and deviation from the perfect diagonal, and indicating prediction errors. The worst case prediction error is reported as about 81%. This suggests that at least one prediction deviates by a significant margin from the actual value. For decision tree, its MSE and MAE are higher than the multiple linear regression, showing that the average absolute error is worse. R squared is 0.2. This is a low value, indicating underperformance. The points in the scatter plot are widely scattered, especially compared to the plot for multiple linear regression. There is no clear pattern or alignment along the ideal diagonal line. The reported maximum error is 155%. It is extremely high and shows that at least one prediction is highly inaccurate. Finally, are the implications of the results. From the results, we can find that weight-based features have the most influence on predictive accuracy. Therefore, abalone farmers and processors should prioritize capturing accurate weight measurement. Sex has a lower predictive power, suggesting that it should be optimal for simplifying field data collection. By deploying machine learning models, stakeholders can significantly reduce the manual effort, thus lowering operational costs. Accurate and scalable predictions ensure that abalone harvesting aligns with maturity level, supporting long-term sustainability in the industry. And these are the analysis for the project. Thanks for watching.